Hello everyone, how's it going? We're about to get started here. Welcome to the EMA Expo 2025. This is the first session of the Expo, and we are going to be dividing it into two presentations for the fundamentals of Ansys Charge Plus and EMC Plus solvers. My name is Aaron Ward, and I'll be your host for today's presentation. Please be advised that to submit any questions you have during today's webinar, please use the Teams webinar Q&A feature. After each presentation, we will address any submitted questions. Should there be any unanswered questions at the end of the webinar, we will address them over email to each individual. We're excited to have two fantastic speakers for today's session. First, you'll hear from Tim McDonald, President of EMA, followed by Brian Newfield, one of our most experienced team members and an Associate Technical Fellow here at EMA. Tim McDonald is a leading expert in electromagnetic modeling and simulation, specializing in multi-physics solutions for EMC, power systems, and space environments. As a key contributor at EMA, he drives innovation in computational electromagnetics, developing advanced techniques for interference analysis, plasma physics, and high-power effects. With extensive experience in EMC Plus and Charge Plus, Tim has helped engineers tackle complex challenges in aerospace, energy, and manufacturing. He is passionate about bridging the gap between ease of use and high-fidelity physics, enabling engineers to model real-world electromagnetic interactions with confidence. Tim regularly presents at industry conferences, sharing insights into the latest advances in simulation and design optimization. Brian Newfield is an associate technical fellow at EMA and lead developer of Ansys Charge Plus. Brian joined EMA in 2013 after doing a postdoctoral fellowship at Los Alamos National Laboratory and earning a PhD in physics from Duke University. He has particular interest in developing and implementing numerical algorithms to support high-level multi-physics simulations. Without further delay, I give you Tim McDonald.
Hello, everyone. Thank you for joining this session today. I'm excited to be here and ready to give the first portion of the presentation. So between Brian and I, we'll talk about some of the fundamentals of the solvers in EMC Plus and Charge Plus. After giving an overall introduction to the software, I'm going to dive into the theory for EMC Plus, and then I'll pass the baton to Brian to talk about some of the Charge Plus solvers. So who is EMA? So EMA has been doing electromagnetic effects for more than 45 years. We have more than 50 technical staff members, many of them PhDs, designated engineering representatives, subject matter experts. We began our history doing Department of Defense development programs and have done work on human spaceflight and have special expertise on civilian aircraft airworthiness certification. That's like FAA certification. And in recent years, we've expanded into automotive electromagnetic compatibility and consumer electronics electromagnetic compatibility. EMA sells our two products that I'll introduce in a moment through Ansys. Ansys is the only place currently that you can purchase the EMA simulation products. In addition, EMA is an Ansys services partner, which means that we can do projects for customers directly for Ansys customers. So to understand the solvers of EMA, I want to talk a little bit fundamentally about the relationship between theory and experiment. So I'm going to quote Terence Tao, maybe the greatest living mathematician that we have right now. So on theory and experiment, he says we need both top down and bottom up. It's an interaction between these. So over time, the observations and the theory and the modeling should both get closer to reality. But initially, they're always far apart to begin with, but you need one to figure out where to push the other. So that's really been fundamental to how we've advanced our simulation technologies at EMA. So we're a company that provides simulation software, as I've talked about, but also has been doing consulting services for our customers for more than 45 years. So that's really given us expertise on actual problems that our customers are facing on the ground. So that the software and the theory that is developed in that software matches up well to what customers are most worried about. In addition, we do testing services at EMA. And over time, that's helped us in-house to validate the software against experimental measurements. And as Terrence Tao said in the quotation, when you first start out, both measurements and theory are somewhat distant from reality. So it's challenging to have theory match experiment, partly because the theory may not match reality, but also the measurement technique may not be perfect. So over time, we get better at both. And currently, we don't know a better way to approach reality than to use both tools in our tool belt, both theory and experiment, to approach reality. So having them collaborate is really the best approach. And of course, when we have consulting and testing services, that help keep those testing focused on the real industrial needs of customers. There's two simulation technologies that are the focus of this session that we'll go through. Ansys EMC Plus is a platform-level electromagnetic modeling tool for design to validation for EMC and related environments. EMC Plus is about extreme geometric complexity, and we'll talk more about that. Ansys Charge Plus is a tool that combines electromagnetic solvers, fluid solvers, particle physics solvers for an easy-to-use multi-physics simulation. So this is a tool that's about extreme multi-physics, but doing so in both an advanced way, but also a way that's approachable and easy to use by users. So the value proposition for EMC Plus, our goal is and has always been to be the fastest time to value. So whether that's simulation time or just the analyst time to build the model, we're always looking for ways to reduce the time between the engineer posing the problem and getting to a solution. So that's not been an overnight thing. It's taken many decades to chip away at some of the technical challenges that get us to where we are today. So the key contributors to that short time to value are the ability to work with extreme geometric complexity by using a forgiving mesh. We use a grid-based mesh. And then we use hybrid subcell solvers. And I'll go into detail in this first hour of this presentation about what some of those subcell solvers are. And that allows us to get the extreme complexity we're after in the shortest period of time possible. And of course, that user interface matters to that. So it has to be intuitive. We have to have automation in those workflows, and then the solver itself needs to allow for high performance simulation on large models. And these days, that tends to mean accelerators like GPUs. All right, so first example of an EMC Plus simulation that we would be going after would be just a basic electromagnetic compatibility of a system. In this case, we have a printed circuit board. It can be a multi-layer board. That board can have components. Those individual traces into nets. In this case, some of those nets terminate on the end of cables. Those cables pass to the edge of the enclosure and then are shielded outside the enclosure. And there's a connector that interfaces the shield of the cables and the cables themselves to the enclosure. And then fields emanate from excitations on the printed circuit board. They may go straight out the apertures in the enclosure to the receive antenna, or they may flow on the cable, go through imperfections in the shield, and then emanate toward the antenna. So there's many things happening. Again, this is indicative of the types of extreme geometric complexity typical of EMC Plus models and the types of things we'll be solving. So I'll talk about some of the fundamental things that allow us to do this type of simulation in this presentation. And some of the later Expo presentations, they'll go through the steps to set this up in the software itself. But today we'll be focused on the theory. The second example that I'm going to show is larger devices. So with EMC Plus, sometimes we're looking at consumer electronic devices or line replaceable units inside larger devices. But EMC Plus, with its extreme geometric complexity, can be used to model full vehicles, cars, industrial equipment, buildings, plants, things of that nature are computationally amenable with EMC Plus. And in this case, this is a specific absorption rate simulation where an antenna that is mounted on the car in the shark fin creates electric fields that couple into the human body model. So just gives another example of full platform extreme geometric complexity that we can pursue with EMC Plus. Charge Plus, which Brian Neufeld's going to talk about in the next session. This is multi-physics and it's co-simulation. The goal with Charge Plus is to be accurate where needed. So it's using some very high fidelity solutions, connecting kinematic solutions with electromagnetic solves and extremely short time steps where needed. And then where you don't need that extreme level of detail, we can relax some of those constraints and go for performance the rest of the time and make it more computationally feasible. This tool can consider gas phase interactions, chemical reactions, and particle physics effects that are critical for plasma dynamics. And you get one user interface, and all of it is well connected and modern in its feel and works well in connection with external databases and other Ansys tools. So an example problem for Charge Plus that we'll hear more about this week, this is a plasma enhanced chemical vapor deposition cell, and we're seeing electrons inside this cell respond to the RF fields that are setting up this plasma. Another example of the use of Charge Plus is using the FDTD simulation in Charge Plus. In this case, that's the ability to model a non-contact ESD arc. So this ESD arc creates a electrofluid interaction, and then we can see how that couples to PCB traces, nets, down to individual interposers to look at the voltage and current induced on those by that nearby non-contact ESD event. So a couple of examples of the types of plasma arcing problems that we might try to solve with Charge Plus. All right, so for the rest of this session, I'm going to talk about some of the advanced concepts and theory for EMC Plus. So first, we're going to talk about some of the history of that. So the first approach to the finite difference time domain, which underpins one of the solvers that's inside EMC Plus, was Kane S. Yee. He was a professor, also worked at Lockheed, and at the time, the innovation was to take the grid of fields in space for electric fields and magnetic fields and offset them by one cell in the grid in X, Y, and Z. And that overcame some limitations of just a naive discretization of Maxwell's equations, where the E and H fields fell on the same grid. And the genius of that and some of the practicality of that can be seen if we just look at the individual step equations. So the step equations are just the discretized versions of Maxwell's equations. So one of those field step equations, the next time step for H in the Z direction is based on E in the Y direction and E in the X direction on either side. So you can see by staggering the grid, H of Z is right here in the center of the face, and the E fields are on the center of the edges. So I need to difference this E sub Y and this E sub Y, and then in the second term, I need to difference this E sub X and this E sub X, and they're as close as possible to being on either side of the H and Z. So the spatial error for that separation is minimized when we stagger the grid. So this is the easiest way to visualize what we mean and why we would put together a Yee grid, named after that professor that I mentioned in the last page. And this method had another big advance by Lamb in 1969, who did the work necessary to derive the condition for stability and the CFL condition and found that as long as certain criteria are met, such as the Courant criteria, which I'll talk about in a little bit, you can guarantee convergence under those circumstances for these equations. So that really gave us the mathematical underpinning to be confident in further developing this tool and being able to use it, knowing that we'll see convergence when those criteria are met. And then the current form of the equations that we use were written by Alan Taflov in 1975. This is the first time we think anyone used the words finite difference time domain. He added interactions with materials, which of course is necessary to do anything practical, and gave us sinusoidal steady state solutions in 2 and 3 dimensions. Then a couple years after that, Merriweather, Holland, and Perala, 1977 and 1978, published the first, as far as we know, the first industrial use of FDTD that made it into the literature. They're at Mission Research Corporation, and then together they founded EMA a few years later, and they were modeling the F-111 aircraft and electromagnetic pulse coupling to that aircraft. And as far as we know, the first practical use or industrial use of FDTD in this case. And so you can see an example. Here's some marketing material from the early days of EMA where an F-16 was modeled with these massive computational cells. And of course, EMA was founded in the computer era where Fortran cards weren't necessarily used after EMA's founding, but those people that founded EMA, they started their career using punch cards. And so really, by the late 70s, the punch cards were not used anymore, and they were using some level of computer graphics, but they certainly saw the advantage of it. There were computer graphics in that, you could type things into a terminal, but back then there was no such thing as CAD or 3D geometry in computers. So they would visualize the aircraft that they built in 2D slices on paper, or in some cases they would visualize it with Legos. Of course, FDTD always reminds people of Legos. And typically from that era, the Fortran code that you use to solve the problem would show up written out in full detail as the appendix to the reports. So of course you would never do that today because you might have hundreds of thousands of lines of code, and that just wouldn't be practical to try to put that in a PDF or a paper report. But that's how they did it in the early days. And even with the primitive codes and the state of computer technology back then, they were able to show fantastic correlation. Just like I talked about in the introduction, our goal here is to get better at experiment and simulation, so both approach reality. And whenever we do a validation on the same platform where the simulation is simulating the same thing we're measuring, such as the MD-80 aircraft, and we have good correlation between the two, we can feel somewhat confident we're on the right path. And so this was shows the power of this technique. Even with early 90s computer hardware, we're able to model full aircraft. So you can imagine this is something that's been continued in the intervening decades, refined, and only improved over time. Certainly a highlight was being on the cover of the IEEE Spectrum magazine. So Spectrum is a cross-discipline IEEE journal. It used to be a physical magazine, maybe it still is, but almost every engineer for many years would get this monthly. And the cover article was here. EMA created solvers to interpret data from aircraft that were intentionally flown into lightning events and instrumented to study lightning. So that was a big deal for EMA. EMA won an award for that, and that was presented to EMA by an astronaut. So you can see in examples of some of these early reports, some of the refinements that they applied. Even as early as 1980, they had the ability to do subcell models like thin gaps. And so you can see this first thin gap model was very primitive, not very sophisticated. If you look at the term It's just a numerical, a single straight line average where you compared how big the gap was compared to the cell size, and you correct your fields. Of course, gap algorithms are more sophisticated these days, but the beginnings of subcell algorithms were present even in those early days of using the technique. And very important one here is thin wire derivation. So as we start to look at conductors and wires, oftentimes they get into a type of energy flowing on them that we could describe as TEM, transverse electric and magnetic fields. And in that case, with a TEM, you can actually derive a voltage and a current. So you can see an I and a V, which are nowhere present in Maxwell's equations, but if they couple to a transmission line, you can derive an I and a V. And so you can see the beginnings of how people would be tempted to combine transmission line theory with full wave electromagnetics when you look at these equations. So even as early as 1980, you see the beginnings of EMA 3D and M-harness being something that would be tempting, tantalizing to the engineers developing these methods. All right. In the next section, we'll talk about some of these key concepts. Now, before we've talked about history, some of the concepts in this section are going to be applicable to you as a user of these tools. Now, certainly as a brand new user, you don't have to know all these details, but as you start diving into these simulations and understanding, hey, why, when I change some of the spatial resolution, does this simulation take longer to run? Well, the practical reason would be the Courant criteria. So I showed earlier the CFL condition where we proved, or where the convergence was proved, and that was published. One of those criteria was the version of the equation that I'm showing here. And basically, this is the time for the speed of propagation, or it could be stated the speed of light in a vacuum, for the speed of light to go from one corner of a cube to the other. Very simple. You can see the C, you can see the cube dimensions. So that is the criteria for stability. You can guarantee FDTD stability if you meet this criteria. What is this delta T? That's the delta T in the step equations. So that's one of the key inputs to FDTD and to EMC plus is the time step. Now, for new users, the time step is set for you automatically. It's intuited in some ways, or it can be an input based on the frequencies that the user is trying to get at. But as you get better at using the tool, it may be important for you to directly input the time steps, or at least understand the time steps. The reason you can't use a giant time step and have the simulation run faster is you may be limited by this criteria. So that's something to keep in mind. The space step, so the discretization in XYZ is directly related to the largest time step we're allowed to do and still have for sure stability. Okay, all of our simulations, we're solving Maxwell's equations in the time domain. But as engineers, we're often interested in the frequency domain response of what we're doing. Most of our EMC tests are posed in the frequency domain. So built into EMC Plus are several discrete Fourier transforms, or as an advanced user, there may be times where you want to do your own discrete Fourier transforms. And discrete Fourier transforms, we use a special case of them, which is the fast Fourier transform, which is amenable to being very fast on modern computer resources. And using those, we have to bear in mind some limitations. Right? We don't want to run our simulations forever. So there'll always be an end time to our simulation. So that end time is going to have some impact on the frequency characteristics of what we're solving. So for one thing, whenever we stop our simulation, there's going to be that end time. That is automatically going to produce some level of windowing in our simulation. So even though a perfectly periodic signal, it could be a perfect sine wave, if you stop it at some point, that's going to have some effect, some truncation will be present on the frequency domain version of what you come up with. And so as we work with Fourier transforms, we need to keep in mind the Fourier transform resolution. So the Nyquist-Shannon sampling theory, if a function x of t contains no frequencies higher than b hertz, they can be completely determined from its ordinates at a sequence of points spaced less than 1 over 2b seconds apart. Basically what this means is we need at least 2 samples per period to resolve the frequency. And if you get anything less than that, you're going to get aliasing. Now you can see it's nicer to have maybe a little bit more than that, but at a minimum we need 2. You can see we're not going to be able to resolve this wave without capturing at least 2 points per period. And then that has an effect on our time step. So if our time step, we want our time step to be smaller than 1 over 2b. Remember, b is the frequency we're trying to resolve. And if you ensure that, you'll make sure that you can resolve those frequencies. So for example, a time step of 1 nanosecond means that we can resolve frequencies up to 500 megahertz. And it's linear in this case. If we reduce our time step by a factor of 10 down to 0.1 nanoseconds, now we can resolve up to 5 gigahertz. So that's the reason when you're using EMC Plus and you're changing your target highest frequency of interest, automatically in the user interface, it's going to adjust your time step to achieve that based on this equation. However, there may be times that you want to dial this up or down. So we do give the users the ability to directly change the time step, but you want to bear this relationship in mind. And if we want, another key thing to keep in mind is if our simulation has a time step that can only resolve up to, say, 500 megahertz, and we send 1 gigahertz energy into that system, that's going to create error. So it's very helpful to ensure that your sources have a highest frequency of interest that's no higher than your time step will allow you to resolve. Now the tool will automatically attempt to create sources for you, Gaussians and derivatives of Gaussians that don't have too much high frequency content in them. But there may be times as an advanced user where you want to create your own source waveforms, or you want to use, for example, measured source waveforms, keeping in mind some of these considerations. For example, you may want to filter your source before you put it in, or you may want to decrease the time step of the simulation to resolve the frequencies that you're after. There's more to the frequency nature, but those are a beginning. Okay, let's talk about meshing in EMC+. So many users may want to start looking at the input files. So when you hit run in EMC+, it's going to create an ASCII, a human readable file on the hard drive. And inside that human readable file, you can see all the specification for the simulation. And it's going to use 3 integers, ijk, that will describe a point in space along XYZ. Now, keep in mind we can have a variable grid, so that means that the grid dimensions may be larger, smaller in different locations, but ijk is going to be telling us where we are on that grid. And these numbers start at the most negative point in the domain space, and so that's defined as 1, 1, 1. And we go from the most negative to the most positive, Imax, Jmax, Kmax, on the opposite corner of that domain. And then we can create voxels in the tool that represent geometry. So ijk by convention are going to refer to the lowermost corner of a voxel, the most negative in X, Y, and Z. And so as we talked about earlier, bear in mind that if we picture a voxel like this, the E fields are going to be on the edges of those voxels. The H fields, though, are going to be centered on the faces of the voxel. So if you're trying to probe something and you know where you are on the voxel, you have to keep in mind that the E fields are going to be pretty close to the edge of that voxel that you define, or exactly at it. But the H fields are always going to be a half cell away. So that can be confusing for users where they're probing, that it's being half cell away, but also it can be confusing that we're always referencing the lowermost in X, Y, and Z. So if you want to probe this edge up here, you're going to go to the lowermost definition of that edge in XYZ to reference that particular U field. Okay, just to give an example of what that looks like. So the ASCII human readable file that I mentioned before has an extension .emin, emin is how we refer to it. Again, it is somewhat human readable. Sometimes these files can be large, but toward the beginning, the header of the file, you can see space steps. And this is going to set our global min, our global max, and our step. This happens to be a fixed grid. If it's a variable grid, this is going to be much more complicated and it's a little bit harder to be human readable. So in this case, the minimum point in 3D space is going to be -2, -2, -2 in millimeter. So you can see it's -2 e to the -3 for each block, -2, -2, -2. And it's specifying X, Y, and Z. And then it's telling us we are going to have 6 steps in the X, Y, and Z direction. And for each, we're going to see that the distance, the step size each is 1 millimeter in each. So again, for a fixed grid problem, you can open up the emin file and see what that looks like. For bodies, you can scroll down in the emin file if you have bodies present, or you can do find in a text editor and you can find the bodies. In this case, it's an isotropic body. It's a metal body, so it's a perfect electrical conductor. There's 2 different ways to describe bodies, 1 and 2 point definitions. In this case, we're talking about the 1 point definition. So you can see at 333, that's going to start in the middle of the domain and it's going to go up 1 cell in each direction. So you can see what the overall domain looks like in the space step section. And in the isotropic body section, we can see what a single volumetric voxel looks like in the emin file. Now, surfaces are a degenerate case of the full 3D voxel. So they're just one part of the voxel. And this is actually somewhat unique to have the ability to work with surfaces and lines, subsets of the voxels. Primitive FDTD tools may be voxel only. Some competitive tools may be voxel only. There's many helpful things in being able to work with surfaces, so the faces of these voxels, as well as the edges of voxels, which are lines. But fundamentally, it's still all using the same voxel definition. So for example, the X normal surface is going to be in the YZ plane. So it's going to be EY, EZ, and it's going to capture the HX field. For the Y normal surface, it's going to be EXZ, EZ, and HY. And for the Z normal surface, it's going to be EX, EY, and HZ. So we're not having to come up with new field definitions to deal with surfaces, but we're just picking the correct set of surfaces to work through in our definitions when they interact with materials. And so you can see, you can search in your emin file to look for isotropic surfaces. And in this case, we're using the 2 point definition. And you can see that we have a normal direction in each case, in this one X, this one Y, this one Z, and you can see how those surface definitions are rotated, and you can see how we're defining the beginning and ends of those surfaces themselves. And then these can be combined, and often are in many simulations. In this case, we have a body. That body has a definition, and then we are defining separately a surface that is a subset of those voxels. But we can take that to our advantage. For example, maybe you have a PCB where you have dielectric that needs a body definition, and we have traces or vias that look like surfaces and we can use larger cells by using a surface definition for them. So even though they're parts of the same voxel, we can control the properties of them when we have materials interacting with the fields in very controlled ways this way, by having separate surface, body, and then ultimately line definitions. There is an order of priority in EMC+, meaning that surfaces have priority over bodies, lines have priority over surfaces, and PEC materials have priority over non-PEC lossy materials. So that allows us to have degenerate definitions and know, based on that order of priority, what is going to be modeled in EMC+. Okay, let's talk about a few more general FDTD concepts. Typically, we don't, in any simulation, want to simulate the entire universe. We want to have some bounds on the edge of what we might call an air box where we stop simulating. One thing that's a little bit different in EMC+ is there's no explicit air box. You define the geometry you want to model, and the solver will automatically assume anything in the domain that you haven't defined as material is what we call background. So you can just separately set the background. You don't have to worry about creating the negative space and the air box manually. And this makes things a little bit easier. We have the ability for the background to be linear. We can go non-linear with the background, but when we do that, we're actually using the charge plus FDTD to have a nonlinear background. And there's 10 different boundary condition types that we can use in EMC+. So, of course, perfect electrical conductor, perfect magnetic conductor. I'm showing here one of the periodic boundary conditions. This is like the original Mario, where Mario runs out of the right and he comes in to the domain on the left-hand side. This can be very useful for example, the people that use FDTD for photonics use periodic boundary conditions all the time. For EMC, we don't use periodic boundary conditions quite as much. We use more something like I'm going to show on the next slide, which is open boundary conditions. And what they're trying to do is simulate open air. So think of this as the analog to the absorbing foam you have in anechoic chambers, where the goal is to absorb the energy and reflect back the minimum amount into the domain. That's the goal of all open boundary conditions, is to absorb everything and have zero reflections, which will affect the results. For example, MER1H, MER1E. MER is not an abbreviation. It's actually the name of a researcher that first developed the MER absorbing boundary condition layers. FEGME is kind of a more advanced version of MER. What we use more commonly is perfectly matched layer, where on the edge of the domain we have a successive series of layers with a slightly different impedance in each layer, which really is conceptually very similar to how anechoic absorbing pyramidal foams work. In the same way, a plane wave approaching those pyramidal foams is seeing a slightly changed impedance as the plane wave moves along the foam. In the same way, that's how PML works on the edge of our boundary condition. Something to keep in mind is PML layers do take computational time. So the more layers you have, the more accuracy you have, less reflection, but it is going to take a little more computational expense. And then let's talk about some of the thin material algorithms. I mentioned before that our grid or Yi-based meshing is one of the superpowers that we use to get extreme geometric complexity. Another one we use is subcell algorithms. So this is where we have things that can represent something that's smaller than the cell size. Remember, I showed a very primitive thin gap and a primitive thin wire derivation. We can actually model thin materials with EMC+. We can model multi-layer materials. We can have a stack up of different layers with different conductivity, with different dielectric properties, different permeability, and all of those layers will have an effective Yi cell material. So in the GUI, you're setting up all of those layers. The solver knows how to combine all of the material properties for those thin layers or for those multiple layers together to make an effective Yi cell property. And we can also do the same thing with gaps and seams. I mentioned before a derivation of the simplest, easiest thin gap algorithm. In this case, the thin gaps and thin seam algorithms have gotten more sophisticated. These days, you can put an arbitrary impedance between two surfaces or between two bodies anywhere you want. And in fact, the mesh engine knows ways to prevent that boundary from shorting things out on very complex geometries. We can have anisotropic materials. What that means is instead of having the same conductivity or same dielectric properties or the same permeability in X, Y, and Z, we can actually define conductivity, permittivity, permeability as a tensor. So we can input those 9 quantities, and a lot of materials are reasonably approximated as isotropic, but not all. For example, carbon fiber materials are a material that are by design anisotropic in their conductivity. So you can imagine in aerospace, using carbon fiber is ubiquitous, so being able to model anisotropic carbon fiber panels is important, and we've validated through some real-world testing carbon fiber panels and their anisotropic properties. Usually the hardest part of using anisotropics is extracting those properties. So out of scope for theory today, but there's some special techniques you can use to extract the conductivity tensor and the other tensors that you need to define those materials. Frequency-dependent materials are possible. Even though it is a time-domain solution, we can model things that are frequency-dependent. On the solver side, there's actually a lot of work that goes into making that happen accurately. So what we need to do is define the permittivity and permeability, which of course include the conductive losses as well as the magnetic losses in this definition, with the real and imaginary parts of those. Those are complex quantities. We first define them as an expansion of terms with parameters. Then an analytical Fourier transform are applied to the expanded definition of mu and epsilon. And we do curve fitting of the frequency domain version of the expansion that is Fourier transformed. So the users can input the real and imaginary parts of permittivity and permeability, and the software has a fitting algorithm will fit that, and the parameters for that fit are the same in both the time and the frequency domain. So once all that math is done for the solver and you have those parameters from the fit, we can use them in the time domain solution. So as a user, all you have to do is input the parameters and hit fit. But on the back end, the solver, there's a lot of work that goes into dealing with frequency domain materials in a time domain solver. Just as a validation, this is just a coax with lossy magnetic material on the inside, and we can compare a finite element method frequency domain tool, HFSS, to EMC plus, and we can see that the frequency domain S parameters, the S21, from one end of that coax to the other when it's forced to go through that magnetic lossy material. We see the losses turn on at the same frequency and the curve looks the same. So we're capturing those frequency dependent effects in a time domain solution, which, as I said, is not easy to achieve, and it's validated here. We talked before about how in a field solver handles all manner of E&H fields, but in certain cases, we can have energy propagate in what we call a TEM, a transverse electric and magnetic wave propagation, in which case it makes sense to look at the definition for voltage and current on that TEM. And a common TEM is just a transmission line that for us often is cables. So almost all devices and interfaces to devices or antennas or other electronics that we see in EMC eventually end in some TEM cell, or we couldn't interface them. So whenever we have cables, we probably, at least at some frequencies, have a TEM mode transmission line. So we're able to use the transmission line equations. And so many years ago, we began the effort of merging the differential equations that solve the telegrapher's equations with the general Maxwell's equations, so that we can have one tool that could solve the full field equations along with the transmission line equations. And as far as we know, this type of hybridization of the telegrapher's equations and the full wave equations in this kind of full no approximation method, bidirectional coupling on the same grid, this has only ever been achieved in EMC Plus that we're aware. And so this gives us a lot of power to use what's good in transmission line theory, which its computational efficiency, its ability to look at something directly that we would measure, like voltages and currents, and couple that directly with the power of a full wave solver, which for EMI EMC, typically the whole point of that domain is something is happening in fields and waves that you can't capture in a traditional SPICE or circuit simulation. So by merging those two together, this is what everybody wants, and so that's really the key differentiator for EMC Plus versus other tools. So this differential equation, it's solving for the matrices for inductance, resistance, capacitance, and conductance. And all of those matrix quantities themselves depend on the cross section of the transmission line or TEM cell. And then once we have done an electrostatic solve to extract the capacitance and inductance matrices, the conductance and the resistance matrices are just inputs. Then we can solve down the line. It now becomes a one-dimensional differential equation to solve, and we solve that in our case using the finite difference time domain method in one dimension, but solving this system of differential equations that we're discretizing. Again, we are offsetting the voltage and the current in this case by 1/2 cell. So the nodes, the voltages on the nodes, the current is 1/2 cell between the voltage nodes. So bear that in mind as you're trying to measure current, that they're always going to measure in the positive direction 1 cell forward on the whatever cable you're trying to measure. And the cell size matches up with the cell size and the FDTD. And then we have to deal with the terminal voltage node, which has a set of boundary conditions that we can deal with. And then the results are the voltages and currents on that transmission line, everywhere on that transmission line. But it's solved, in this case, self-consistently with the E and H's everywhere else in the problem. So we have one universal solution, one coupled set of differential equations, and it's the electric field that we couple the full wave to the transmission line equations. And so typically when you run an EMC Plus simulation that includes mHarness, which is the name given to our multi-conductor transmission line solver, the first step that happens is it'll look at the cross-section at each portion of the cable, and it will do a quick electrostatic solve to get the capacitance and the inductance matrices. And then once that's held, it'll start stepping the transmission line equations at the same time as the full wave Maxwell's equations. We do some things by fully universally coupling our transmission line theory to our full wave solver. We can do some things that you can't do if you cheat. For example, you can solve a full wave solver and just pass something in a separated way to your multi-conductor transmission line solver. This kind of two-step approach is something some competitors take, but they miss out on the ability to do some tricks that violate traditional transmission line theory. For example, we can let wires break out of shields. We can have shields break out of overbraids. We can have conductors terminate on each other. So the other tools that can't do this can't do some pretty fundamental things in electronics. For example, we can join twisted shielded pairs at one end of the wire. And in fact, if you can't ever break a wire out of a shield, how does it ever interface the electronics on the termination on the printed circuit boards? So we thought from the beginning that a full universal solution was essential. It was not easy to achieve the unification of the transmission line solver and the full wave solver, but now that that is done, industry reaps the benefits of the ability to do some of these things. So typically there are system levels involved with transmission line theory. So you make some assumption that the TEM cell inside of shields are independent from the TEM that's outside of those shields. And so the only communication that happens between those system levels occurs through the transfer impedance, which is a quantity used to describe the imperfection of shields that allow for coupling through things like braided cables. And when we hybridize them together, we're solving the cables and the 3D geometry on the same grid. So the Y grid that we create for M-harness is the same grid, Y grid that we create for the full FDTD that we call EMA 3D. So in an M-harness termination example type, when users are creating the lines as a user interface, they can define those terminations. So typically people will put a circuit boundary condition whenever a line terminates on a surface. So that allows us to put a linear component or a combination of linear components, resistors, inductors, capacitors on the interface between that transmission line and that surface. So that's what allows, for example, the cable to terminate on the PCB trace or something else. Now we take advantage of some shortcuts. If a transmission line passes through a surface and the line is not split at that surface, then there's no electrical connection between the transmission line and that surface. That allows us to pass through as if it's a clean bulkhead. If we split the transmission line at the surface, we assume there's electrical connection at that surface. So that means by thoughtfully splitting or joining your lines, defining your transmission line, you can control the nature of the bonding at those bulkheads, which is essential in EMC to getting the right answer and matching up to your design. And as I mentioned before, one of the key features that surprisingly many people will try to use transmission line theory tools that don't have the ability to do something very basic, which is to break conductors out of shields. So this is just a canonical example. This might be a patch antenna, this might be a printed circuit board, but in this case we have a lower patch and an upper patch on each side, where the upper patch and lower patch are separated by a non-conductive dielectric like FR4. The center pin of the coax are connected to the top. The shield of the coax are connected to the bottom on both sides. You can only do this if you have a self-consistent transmission line theory that couples fully to the full wave solver. And we can even break out in air. So that basically means putting a termination and just having nothing connected to that termination. So that just, sometimes that happens in electronics or in vehicles where you have a shield that doesn't have a nice termination. What's inside that shield just breaks out electrically. So we can model that situation. All right, now I'd like to summarize some recent feature updates. It's really hard to talk about EMC Plus without talking about GPUs. So EMC Plus supports GPU acceleration. It runs on Linux. This slide is actually incorrect. It runs on both Linux and Windows platforms. I apologize for that mistake. It can be run on multiple GPUs in parallel on Linux. One GPU is supported on Windows, and you can complete simulation in a significantly shorter time compared to CPU simulation. So this can be scaled up to hundreds of times faster compared to multi-core CPU alone. So the equivalent GPU is faster than a typical CPU that's in an engineering workstation, and GPU machines can be scaled up to more power and more efficiency than the equivalent CPU cluster. So whether you're on commodity hardware like a simple laptop with a GPU, or you're on very expensive high-performance computing. For our FDTD, the GPU always performs better than the equivalent CPU in size and cost. So just to give an example, printed circuit board simulation EMC plus, broadband 3D simulation at 16.7 times faster on GPU versus CPU, and this full car runs about 11.9 times faster on the GPU versus a CPU. Another recent update is a conformal boundary approximation. So what this allows you to do, we talked before, one of the advantages of FDTD is our ability to solve in cases extreme geometric complexity by using a grid-based cell. That grid-based algorithm for meshing can introduce staircasing, which can affect results. This is conformal boundary approximation for surfaces is one way that we can reduce some of the numerical issues with staircasing. So that gives you a tool to use to solve that problem. Another is cable twisting. So whenever we look at cables defined in electronics or vehicles or aircraft, often differential pairs are twisted together. It's a very effective way to reduce EMI. We now have the ability to automate that twisting in the solver side, which makes life easier for users trying to specify twisted shielded pairs. And I alluded to this before, is we've now got the ability to model thin layer materials with where this is a subcell feature where you can specify one surface, which is one part of the yeast cell that looks like a surface on the edge of the yeast cells. And we can have that one yeast cell model multiple layers stacked up together. It determines the effective properties. And so you could use a much larger cell than you're modeling and be much more computationally efficient with the multi-layer tool. Okay, that brings to an end some of the details of the theory behind the solvers in EMC Plus, which are EMA 3D and M-harness. And next, we are going to talk about some of the theory behind the solvers in Charge Plus.
Thank you for that, Tim. And before we move on to the next presentation, we're going to go over a couple of questions. So the first question is, can you explain more about the coupling between EMA 3D and M-harness? Does it go from EMA 3D to M-harness, or does it go both directions?
Yeah, the coupling is bidirectional, so that because they're solved on the same grid and they're solved inside the same binary, we use the E field in the direction of the transmission line theory. So bear in mind, there's a relationship between the E and H fields that's defined based on the fact that it's propagating in TEM mode. So if the criteria are met for it to be in TEM propagation, which for most cables below a certain frequency, you're going to be in TEM propagation. We have the ability to solve them on the same time, and that energy can go bidirectional. So what you can imagine, you can have a cable that enters an enclosure, you have energy on the outside of the enclosure coupled to the cable, flow on the cable and conduct inside the enclosure and radiate off the cable. Very common thing that happens in an EMC simulation. Only a bidirectional solver would be able to resolve that particular situation.
Great, thank you for that, Tim. The next question is from Matt. 3D animators use voxels for volume simulations, smoke, fire, rain, sunlight, etc. How much does the EMC plus FTDD simulation overlap with these tools? Are you pulling ideas from their industry? Is there any other way around? Is a 3D animator's sunlight animation or simulation solving Maxwell's equations?
Yeah, that's a good question. So, of course, we see voxels all the time. If you have kids playing Minecraft, voxels are a useful way to represent data, setting it up on a grid like that. So in one case where we can directly use voxels is when we're doing the specific absorption rate to look at the coupling to human tissue. body tissues from electromagnetic fields. That's a case where you may want to set the density field in 3D in voxels directly from that external data source. Our solver sets up well to that. As other applications present themselves, there would be the ability to do voxel by voxel setting of parameters in the future as well.
Great, thank you for that. And then the next question is also for Matt. Is the wire twisting feature something new to the 2025 release? I recall this being semi-challenging when discussing its implementation in early 29-24 with EMA folks.
Absolutely. So that's a 25R1 feature. So that was released in January, and that was a very common user request to have the ability to automate that. So it's so much easier now, and the cables don't have to be subdivided to achieve that twisting.
Great, thank you, Tim. And then one more question from John. Can you speak to work you've done to validate your software?
Yeah, and so there'll be a lot of that coming up in some of the future presentations. The focus today was on some of the theory and the software, so we'll see a little bit of the experiment as we move forward in Expo. But I showed an example of validation from the 90s where we took the MD80 measurement for the lightning coupling in experimental ground lightning testing and compared that to the simulation and had very good correlation. The FAA allowed Douglas Aircraft at the time to certify aircraft using simulation based on that good correlation. And I talked about the F-106 program where aircraft were flown into storms intentionally to be struck by lightning, and EMA did validation. But that's just the tip of the iceberg. We've been validating full devices, electronic devices, and full platforms. In the decades since then, we have many published validations. We have many more validations that we can't talk about because they're proprietary. So that's really been central to what we do with our tool, is being able to advance theory and experiment together, getting better at measurement, getting better at simulation techniques so that we understand reality better. And so I would say we do both measurement and simulation better than we did in the 90s. And you'll see some more examples of validation as Expo goes forward.
Great, thank you for all of those answers. I think we'll give it another minute or so to see if anyone has any last minute questions, and then we'll move on to the next presentation. Okay, it seems like no one else has any questions. So with that, we have Brian Newfield presenting next, and I'll let you take it from here, Brian.
Thank you. And then let's see, do I need a, Tim got me there. Okay, I'm going to present this slideshow here. Let's switch it. Okay, so yeah, thank you, Aaron. My name is Brian Neufeld, and glad to present some of the, I guess, technical underpinnings for Ansys Charge Plus, particularly looking at the FEM and particle kinematics part of that. I wanted to also mention Jacob Johnson, Colin Brennan, Dustin Ursery, and Griffin Kowash, who contribute to some of the material we'll see today, and added contributed a few slides as well. Appreciate their hard work. So a little overview here. So I'm going to present from the perspective of the, or my perspective, the lead developer perspective. And so I'm going to give a little bit of a historical background. These are not necessarily EMA official benchmarks or progression, but it's kind of my view of how things have unfolded. And then I'll start to get a little bit more into some of the technical aspects. Try not to get so detailed with anything that it gets to be like boring, but or overwhelming, but just give some of the basics. Certainly can submit questions that can be answered at the end of the presentation or even later on. And then so there's things about the fields, the particle dynamics, and then look at some of the applications. And in some ways, that's probably the most interesting part of it. A bit on the acceleration and performance, and kind of our near-term outlook. So yeah, so Tim gave some presentation or some of his presentation to the background of the EMA 3D FDTD development, and so I wanted to give a little bit of that as well. And from my perspective, this story of Charge Plus probably goes back to about 2008. And that was when, I believe that's when EMA started supporting the Orion space program. And that was before I was at EMA. There wasn't actual solver development at that time, but there was a context started to come together of kind of this challenge where the analyzing the threat of spacecraft environmental effects, and some of the dynamics that go on there are something that we started looking at a long time ago, and eventually that same type of system analysis or environmental analysis has expanded into kind of a broader and more generic software tool that addresses a similar type of problem, but in a lot of different contexts. Okay, so I've just told my screen isn't sharing, so let me make sure I've got this, and apologize. Yes, so anyway, so I'm sharing these slides, sorry about that. Yes, hopefully you can see that now. And so anyway, so that is kind of the background here, and that's kind of where I see or had viewed us starting. And so now one of the things about it, the common theme that, and yeah, and I didn't mention that the specific analysis I think that we started with was the surface charging simulations, and then eventually we also looked at internal charging, and even back, I think in my early days at EMA, I know that we had started to understand the importance of mission ephemeris and incorporating that specifically into this kind of analysis. And so we'll talk about some more of that and how that is even reflected today in Charge Plus. But that's kind of some of the background. Now, the common theme there was that this coupling of particles and fields. And I think in some ways that's, kind of true of probably any electromagnetic analysis, but in some ways I think Charge Plus especially, because we're typically looking at some sort of particle dynamic, particle kinematic that becomes a very important part of the system, and then that drives fields, and so there's this interaction that goes back and forth. Particles driving fields, fields driving particles, and then I think that's kind of what's unique in terms of the Charge Plus challenge, if you will, or what we try to solve. And so and in spacecraft environment, this of course it's really clear, right? Because you have some kind of environment with charged particles a lot of times. It could be other types of radiation, but that's a general theme. And so and in terms of the spacecraft analysis, I put a few things here. You could have particle kinematics or transport phenomena. So it could be like PIC environment that drives a surface charging problem, or some sort of transport phenomena that drives a internal charging problem. A thermal distribution is a lot of times looked at in a surface charging problem. Some kind of Maxwellian or non-Maxwellian system that has an approximate temperature. But all of these have some kind of description of particles that drive then a system response. And then I added in there the circuit dynamics. depending on what you have in your system, for example, the different chassis and things like that. And so and we've all of these things on the left in the bullet points are now things that are in Charge Plus, although perhaps in a more generic context. Now, I had mentioned we had started probably all the way back at roughly 2008 in terms of not development, but analysis of these kind of systems in the space environments context. But then I would say, from my perspective, solver development probably began with what we had called at the time EMA 3D internal, which was focused on the internal charging space environments. And even though this is somewhat of a niche application in terms of the industry and the scenarios that you're looking at, the technology that goes into it is actually pretty somewhat sophisticated, in that there's this coupling of transport with field calculations. And so even from that early time, we had tried to address this problem. We had worked with Larry Lallement at Lockheed Martin, and had some other opportunities to explore this kind of analysis, and had used tried to evaluate fields on shielded cable in this particular case. But the idea would be that your system is exposed to some spectrum, some flux of charged particles, probably electrons, and then you want to evaluate the fields, potential fields inside the system to see where vulnerabilities for discharge could be, especially discharge. And so, okay, so now looking kind of past the history, and now starting to look kind of where the solver is today in terms of Charge Plus solver. So I've got this sort of Venn diagram, I guess, or sort of this overlap here where we have the different arrows. So we have an EM solver that is could be either quasi-static or full wave, and I added in there surface charging. So surface charging is part of the Charge Plus software, and it's a little bit different than the finite element solver. It's used as a boundary element method, but I put it in here. So these are all kind of fields in that one on the kind of on the right here, and then on the left I've put our particles. And so and it's easy just to write these terms down, and a lot goes behind them, and so but in terms of trying to encapsulate it, that's how we would maybe write it. So we'd have particle and cell, analytical plasma environments, and particle transport in terms of particle description. And we'll discuss each of those more later, but the kinetic support on the bottom left, lower left side is really important, and that is probably an understatement of what it does, because it drives a big portion of our particle and cell. There's all kinds of reactions that we support, and those drive a lot of the particle and cell dynamics. But those particles feed the fields, and the fields feed the particles, and they go back and forth, and it becomes a very complicated system sometimes to try to describe. And then I put here in the middle, that's our Navier-Stokes, or fluid system, fluid dynamics. And to me, that one's kind of like somewhere in between particle and fields, because the fields themselves are the particles in that case, and sometimes it can be a very powerful way to approximate a system of particles. And so in terms of challenges, I think the time and spatial resolution, the physics scales that we try to piece together, is a big part of the challenge. And so for many of the applications of interest, there's a Debye scale involved, which is the scale at which maybe a system of charged particles, a plasma, has at which the screening takes place. And a lot of times that scale is important for the stability of a system. However, the Debye scale for many of our problems can vary quite a bit during a simulation, going from maybe something that would be manageable with a mesh, like maybe a millimeter, to something that could become like a nanometer type resolution. So it can be very hard to balance that kind of variation. And then the time steps as well. We just like Tim was mentioning with the finite difference, there is similarly a current condition. It's a bit different depending on the situation, but it's basically the smallest resolution in our mesh sets a current type condition, and then but then particle and cell needs to be able to have small enough time steps so that basically a particle doesn't travel through multiple mesh elements in a given time step. So all of these things make it a really hard problem in terms of some of these applications that we look at. And then the computational efficiency is always a big challenge. Tim had mentioned that with the GPU acceleration before. I think for the charge plus side, there's a unique challenge because there's so many different types of algorithms that have to work together, and they may not all be as amenable to the same acceleration approach. So you have a different ways of trying to keep the system efficient, and then we have I think a challenge is just our module integration. We have different modules that could each function independently. So this would include particle and cell, electromagnetic solver, surface charging, transport, but then and then the fluid solver. But then we want to have what makes this a valuable software tool is that the different modules can talk together and work together. And so having those act in a reliable and efficient way is another challenge that we try to face. And so now I'll switch to some of the implementation. And so what we had mentioned before, I think Tim showed an FDTD voxel. So I guess it's fair that I can show a tetrahedral element. So we use finite element meshes for the charge plus part of it. There is an FDTD part of charge plus, but I'm not focusing on that today. So for the FEM stuff that we use for a lot of our problems, we use a finite element mesh. So what I've included here is the tetrahedral mesh. It's the simplest volume mesh in a finite element mesh, but it's actually quite versatile because many of the other mesh elements can be decomposed into these as well. So the finite element mesh is very versatile in terms of modeling complex geometry. So I just have some kind of stock image on the right of a finite element mesh. This one, you're only really seeing a 2D mesh, but it shows you how the mesh resolution can vary. You can capture these surfaces and curvatures, which is great, but it tends to be harder to solve for numerically than a finite difference because you can't simplify the derivatives like you could if you have a finite difference. You can sort of write down what a derivative means there in a simple way, but with the finite element mesh, you don't have something that straightforward. So there's a different kind of different numerical challenge to it. Just a caveat, we have a kinetic sheath model that uses a finite difference approach. And then, as I mentioned before, the surface charging uses a boundary element method. So those are the kind of the exceptions to the finite element mesh. But from here on out, we'll talk mostly about a finite element mesh. And so we mentioned before that we combine particle dynamics and fields. And so for many of the applications, whenever we have, particularly for particle and cell and particle transport, we have to have some kind of real-time mapping between the mesh and the particles. And so the arrows done below or added below kind of indicate where some particle might be in the system. You could imagine those arrows are some electron propagating into the system and stopping at some point there where the arrow ends. So how would you tell the system, your finite element system, that there's a particle, and then how do you tell it efficiently where that particle is? So that's a big challenge, especially when you're talking about this happening like maybe millions of times in a simulation or many millions of times. It has to be done effectively and efficiently. And so for our transport, we use a spatial partitioning, like an octree, and that tends to be efficient enough for those kind of like internal charging applications. For PIC, it's such an important part of the dynamic of the system to make it efficient. We actually typically don't use an octree for that. We use a different type of mapping that uses the history of a particle's trajectory to keep track in the system. But that becomes an important part of a lot of what we do, is to be able to efficiently keep track of particles and have fields evaluated based in real time on a particle location, and then those fields in turn can modify the particles. And so just a slide or two here on the finite element approach. So if we write down some differential equation, and then we integrate this. So it's different than the finite difference, where you're kind of writing down these derivatives explicitly. Here we're writing it as an integral. And so the typical approach is that you would multiply by some test function, and then you integrate over the simulation domain. And what's nice here is that you don't have to have a regularized mesh. You're integrating element by element, which is great. And then the other part that becomes convenient or makes it a manageable problem is that we can write these test functions or as basis functions. So we write the whole system in terms of these finite element basis functions, and they're not necessarily, they're in some ways they're easy to write down. It starts to become cumbersome to work with them at some point, because depending what all you're trying to do, but it gives you a starting point. It gives you something you can work with. You can look up these basis functions for different systems, different types of elements. And then the other thing that you have to do is an integration by parts. You don't necessarily have to always do that, but for the second order derivative, like we've written here for this kind of Poisson equation, is that you have to integrate by parts if you want to use the typical basis functions. And so it leaves you with a boundary term, and so you have an option for Dirichlet or Neumann boundary conditions. And so this is a general approach, and of course this is like the simplest equation that we would model, but it gives a good feel for what goes into that kind of derivation. And so we test our implementation. One way is to use a method of manufactured solutions. We have a driving term. So like in this last slide, if you take a right-hand side, here this would be, so like a charged density term for a Poisson equation, but that instead you could pick, instead of using a physical distribution of charge, you could pick something that you know is supposed to result in a certain solution, and then check the accuracy of the solver for that. And so here's a couple examples of on a unit cube. We're just showing, of course, a cross section, but this would be a a three-dimensional cube, and we can calculate the error of the solver based on what the exact solution should be. And so it's a powerful way that we can test the implementation and make sure that we're solving things accurately. One of the things that I added here in the slides was our adaptive mesh algorithm. Don't have any equations or anything here, but I just wanted to give a sense of what we had added, because it's such an important part of how we model these systems to be able to resolve the spatial resolution in certain contexts. And so what our solver can do is take a mesh. So in this case, I don't have the unaltered mesh completely shown, but you could imagine the initial mesh was like you would see in the left and top in the middle panel here. And then because so many of the dynamics in certain systems, plasma systems, gets centered or gets compressed towards the boundaries, what we can do is add, the solver will add these layers, small layers around or on the relevant surfaces that the user's interested in. And that's a powerful approach, because it allows you to get more stability in certain regions of the model without having to add a huge computational overhead to the rest of the model. And the one on the right there is similar to the one on the far left. It's just that the algorithm also allows to have the whole mesh deform. You can, if you look carefully, you can see how the mesh deforms in response to the adaptive layers on the boundaries. So it's kind of a powerful way we can help resolve more of the system. So looking at the particle side of Ansys Charge Plus. So we mentioned before that the particles play a huge role in stability, driving systems, and also in stability. Stability is such a big part of what we do in terms of plasma applications, because when the particles drive fields and fields drive particles, things can easily become unstable, and so it's a real challenge for many applications. But we have particle transport. We've done a lot with that in the last few years for the rad-hard side of it. Colin Brennan has done a great work there. I'm not going to talk about the analytical plasma environments just because I ran out of time, but for surface charging, we support different types of environments. These are all kind of an analytical type environment, but still very important for certain applications. And then we do many of our applications use the particle and cell module, and this would include things like discharges, RF plasma, surface charging, electron emission. Okay, so particle transport, we co-simulate with Geant 4, which is one of the respected transport codes, open source codes. And as mentioned before, there's a mapping to finite element mesh when fields are desired. We also have the ability to run standalone transport, but everything is done or can be done at least on a per time step basis. So there's co-simulation going on, and you can actually have the option to have fields affect the fields calculated on the mesh. The FIM mesh can actually alter the incident spectrum if the user wants. And then as mentioned before, we had known for a long time, or felt like for a long time, that having ephemeris level fidelity is really powerful for so many space applications. And Charge Plus integrates with SDK to generate ephemeris level spectrum inputs. It's a really powerful combination of tools that can be used to really do accurate engineering work and evaluation of space environment threat. And then I put on there as well some of the updates for the rad-hard analysis. So Particle and cell, we've done a lot of work there over the last few years. Couples, again, to the FEM and surface charging. And one thing I haven't really emphasized and probably should have more, and we'll see some of this in the applications in a minute, but just the broad support for reaction and scattering rates. We're not necessarily just looking to have a system of particles that generate fields and move around. Most of these applications have some kind of reactions going on that are driving the system, and that adds to the complexity, but also adds to the value of what the software can do, and it becomes very complicated. I don't do as many of the applications as some of our engineers do. I focus on the solver part, but I've seen problems where they might have 70 or 80 reaction rates, and it's just really amazing what they put together. And our UI supports so much of that too. And then electron emission, we'll look at a pretty cool application of that in a few minutes. But from surfaces having, there's all kinds of models that have these electron emissions, but the idea is that you might have a field or a temperature on a surface that then results in real-time updates to the PIC system based on emission from these surfaces. And there's all kinds of amazing physics that goes on underneath that. And then we do have a sheath module as well that is important for the high density systems. That is like an approximation. It'd be very hard to model sheath resolutions in a mesh and maintain computational efficiency. So we have this sheath module that helps stabilize the system at boundaries. So I focused here on this energy conserving semi-implicit method. Some equations here, probably hard to digest in one slide, but just a description. So the idea was that it's from a paper that LaPenta wrote in 2016, and we call it, or he calls it, an energy conserving semi-implicit algorithm, and for short we just call it ESIM, usually ECSIM. But the idea is that there's a system that can completely conserve the energy between particles and fields within a PIC system. It's a very powerful idea because, as we mentioned several times, the particles and the fields kind of go back and forth together. So could you, I guess the challenge would be, could you set up a system that could guarantee to conserve the total sum of kinetic energy plus field energy? So the one or the other might change, but the total sum between the two should stay the same. And what it shows in this paper is that this algorithm is unconditionally stable. So in other words, even if the Debye length is not resolved in the mesh, this simulation will remain stable. And this is not true in explicit PIC. Systems can go stable and do go unstable, I should say, when this Debye length is not resolved. But this is a very powerful algorithm, and some of the equations are shown there, but the idea, the core idea for it is in the stepping equations. And there's the implicit part is that you're evaluating fields at a time step, the plus half time step. So in other words, you're incorporating the E field into the equations of motion such that you're adding a term into your Maxwell's equations, and then you get this mass matrix term that's shown here. And so, but it's a very powerful algorithm, and here's an example where we run a simulation for a system. This is a structured chamber model, but the idea here is that we're tracking, we use this ECSIM, and we track the total energy in the system. And so there's reflections on the walls of the system. These would be elastic reflections. And then there would be no boundary condition in terms of like a potential driving the system, just fields, charged particles with motion that interact together. And you see what happens is that there's starts out with basically all kinetic energy, and then the kinetic energy drops some as the fields develop in the system, and there's some fields, but it all maintains the same total energy. So it's a really cool formalism, and helps with a lot of stability issues. So let's look at some applications, and I want to first look at some discharges. This I got to give credit to Jacob Johnson. He's done so much work on some of these interesting discharge problems and plasma conductivity. But he's added some stuff here that shows how the UI lets a user define a bunch of different reaction rates. There's just so many things that go on in these systems, and they're actually critical, as he says, to have all these different reactions to get validation with what's seen experimentally. But this allows the user to support high fidelity reactions, and it also has analytic definition when the cross-section data is not available. And so as I mentioned before, in these models, there's a plasma conductivity, which is a descriptor of how the charge particle distribution is interacting. And to get the plasma conductivity is very important for getting the voltage drop after the breakdown occurs. So he's included this animation, which I'll run. So he's got this system driven by a current source, and he tries to replicate the experiment in a reference paper on the breakdown voltage. You can see the electron density there as the breakdown occurs. Really cool stuff. This is all being simulated. He's got the potential, and then he's able to actually get an error within 3% of the reported breakdown voltage. So really accurate simulation. Really impressive work. So run it one more time there. You can just see it again. And so looking ahead for some of the discharge applications, more complicated gases, three-body reactions, relativistic corrections, an AC signal, surface reactions. That's something we've been working hard on, and we keep just adding complexity. And so a lot of cool things going on with that. For electron emission, I want to mention Dustin Ursery, who's worked really hard on some of this. So we have some cool animation here as well, but this was again like the idea of the temperature in this case. The electron emission starts to occur in a system, and there's some work function there, and the fields as well can modify that. And so this is a particular model of field enhanced thermionic emission, the Schottky formula. And again, the UI helps a lot with this. This is an electron gun using this emission. It's a pretty cool system. Goes through this lensing apparatus, and let's see, I could play it one more time there. And all of this gets driven by the surface emission, electron emission. There's like some boundary driver, potential boundary driver there, and and then there's electron emission that occurs. One of the new features here just recently that will also be should be in, well, I don't know, I don't want to say what's going to be in release, but this was something we added recently, space charge limited emission, really complicated analysis, has relativistic corrections. It's been carefully analyzed and tested. Just a really sophisticated way to model this kind of dynamic in the system. And then and then you can have actually ion emission as well. And then we've done a lot of work on the angular distribution, so it doesn't have to necessarily be just a simple normal emission. There's other emission distributions, and these can affect or can be reflective of how different surface materials are. So it's yeah, there's been a lot of advancement there. Okay, so now looking at some transport applications. For the 25 R2 release, we have a lot of improvements for particle transport have been done, and these are really helpful for engineers that want to do rad hard analysis and have been don't necessarily need the full simulation infrastructure that would go with the complicated field calculations. And this standalone transport can be quite a bit faster. It's only a surface mesh requirement, and that's also a big help for certain types of analysis. And they can also be actually easier to generate and faster. So here's an example of some scoring volume results, ionizing dose. And this is obviously a really complicated looking system, but it was something that was able to be done with the standalone transport and get some of this feedback, engineering feedback for a complicated electronics box. And by default, you get charge, dose, and fluence. And then there's an outlook for adding the GPU accelerated electromagnetic physics list. So those who are interested in highly complex rad hard analysis, this would be a really helpful feature that should be coming up perhaps by the next release cycle. Something I wanted to include was on our RF plasma simulations and circuit solver module. So one of the things that over the last few months that we had really been excited about was our ability to model capacitively coupled plasmas. This, as mentioned before, was one of these systems that varies over a lot of orders of magnitude in terms of the density and temperatures as well. But the stability is really tough. For a system like that. The biscale can easily be 4 or 5 orders of magnitude smaller at saturation than it is at initial condition. And so one of the things we added, so the EC-SIM mentioned before is a big part of modeling these systems and helps with stability, but we also added a circuit solver module. Tim had mentioned before, how the FDTD code has such powerful transmission line coupling and things like that. But we have this circuit solver module that couples to the boundary conditions. And so you can have like a power boundary condition or some sort of voltage condition, or resistive, I should say, resistive boundary condition. And the voltage varies as the system evolves. So this was one of our validation papers or validation simulations with the Gaseous Electronics Conference RF reference cell. This is a system of argon that ionizes as it heats up, driven by an RF source. And Greg Wilson, one of our application engineers, put this together. We added a smoothing term to our PIC, EC-SIM PIC algorithm. And so there's a lot of things going on there. It's neat to see it match up pretty well to the paper. I wanted to include this is the animation he generated for some of this. You have, he's got the argon density, electron temperature, electron density, and potential all going at the same time and this happens over hundreds and hundreds of cycles. We're just showing a few, but it takes a very long simulation to get the kind of the steady state version of this problem, because it's a lot of it's because of the reaction rates that are going on. But you get this kind of off-centered radial distribution for the ions and electrons in that system. Let's see here. Okay. Yeah, just let it run out here. You can just kind of watch it. Okay. And so one last slide regarding this was this system that shows a self-biasing using our circuit solver boundary condition. So this shows the circuit solver actually adjusting to the charge incident at the boundary, and then so the baseline signal, which would just been a sinusoid, then gets shifted with this biasing term. So the circuit solver module provides a lot of power to or a lot of usefulness to keep a for engineering in the sense of like a power or some way of modeling the boundary of the system and how that changes over time of whatever's driving the system based on the system itself. So a few things on the acceleration and testing. We did a solver refactor in the first half of this year. We've been trying to improve both the memory and simulation effectiveness of our simulations. We looked a lot at our MPI structure and how we do data exchanges and memory storage. And we've also added over the last few years, and maybe over the last year especially, done a lot of improvements in our testing framework. We have a bunch of tests that get run anytime there's a push to the code base. And that also tracks performance metrics. One of the neat slides or neat plots here is looking at one of our PIC tests at the runtime and the memory usage over the last basically year, maybe a little over a year. So you can see the runtime for this PIC model, that one of our benchmark models, has dropped probably by a factor of 3, and then the memory usage is actually down by probably, it's more than that. That might even be a factor of 10. So really worked hard on that. And here's one other benchmark test. I have two more actually. This one had 144,292 tetrahedral elements, and going back to March 13th, 2024 to the most recent. This shows the scaling with processors. The red line doesn't show a sharp drop off with processors. I think it's because the actual solve time starts to become minimal and the initialization kind of takes over, but you can see there's a pretty significant improvement. And then this was one of the examples using a more complicated model, and this one shows a really good scaling with the number of processors, really good parallel scaling. So just to kind of wrap it up here, goals and near-term outlook. We want to get the GPU accelerations added. That hopefully would provide some really good performance improvement and would be straightforward to implement. Looking at some more sophisticated methods in the finite element solver that will help with scaling over large scale problems. So in other words, if your model goes from 100,000 elements to 1,000,000 elements, does the solver converge as efficiently for that system, the 10 times larger system? And for the multi-grid methods, the answer is yes, it would. It's hard to implement, but it's complex, but it could provide great scaling for very large problems. Looking at some things with our basis functions as well, and then and continuing to work on our applications, mini plasma applications. We have focus on some antenna work and the rad hard stuff I mentioned before. So that's the end of the slides, but thank you for everyone that joined today, the meeting, and certainly can open it up for questions.
Great, thank you so much, Brian. Really appreciate that. And yeah, as you said, we'll go into the questions now. So the first one is, when someone When should someone use the boundary element method versus the finite element method?
Yeah, the boundary element method is a powerful or is convenient tool for doing surface charging problems, and for many of the systems where you don't necessarily have to um, track the interaction of charged particles with the surface with high fidelity, that can be the way to go. But we can also support that traditional surface charging problem using the finite element method, where you actually mesh the surface, and that can be a way to track things like electric field distribution or charged particle interaction with the surface. So probably for those more, for the user that needs more sophisticated feedback, that would probably be the way to go.
Great, thank you so much. The next question is, for someone who is setting up a simulation, how would they know the convergence tolerance?
Yeah, that's a good question. We have a default in our solver that goes to, I believe it's 10 to the minus 18 or 16, which is a pretty good one. That's looking at convergence of the solution norm over time. But user could always increase the tolerance and see when the solution is maybe on a test model, could always try increasing it to see if the solution changes. But I think the default around 10 to the minus 20 is a good convergence tolerance for many problems.
Great. Next question is, wouldn't the Courant criteria for the particles result in incredibly small time steps relative to what one would expect for a quasi-static solver? For all but extremely low particle temperatures, it doesn't take much temperature for most particles to have time steps on the order of many kilometers per second.
Yeah, it depends. Yeah, it certainly depends on the system. And we have quasi-static and full wave solver, but it just depends on the system. Sometimes the system we look at maybe the pick requires something like 10 to the minus 10, 10 to the minus 11 seconds per time step. So yeah, it certainly is a challenge in problems, but it's actually the pick solver itself actually calculates the necessary time steps. So even if the user might set up a system at like a nanosecond time step, which is common for a lot of plasma applications, something like in the megahertz. They would the pick solver makes sure that the internal time stepping size for the pick update respects that condition.
Great, thank you. The next question, is the energy of the incident particles tracked as it travels through the depth of the material, or is it determined at the time the particle enters the material? How far, perhaps quantified in number of cells, will it travel? It seems like this would make a difference in the accuracy for situations where there are large changes in material density in the stack up.
Mm-hmm. I assume this would be in reference to a transport problem, maybe internal charging. I could be, if I'm wrong on that, feel free to send a follow-up. But yeah, so the incident energy of the particle would be, in that case, would be set at the spectrum. It's possible that there could be some E-field corrections to that, and then yeah, as the particle transport happens, then you would have at each track in the system, you would have an update to the energy. But it would respect the density. Like if there is a variation, you could model something like that with multiple layers and get a change in the density. It might be tricky to get like an analytic description of a density as a function of distance. We haven't necessarily looked at that, but um, there is a lot of versatility in modeling that kind of behavior.
Great, thanks so much. The next question is from John. Can you provide an example of when the circuit solver boundary condition would be used?
Yeah, so the two that come to my mind, there might be a lot of them. I've seen actually in some of the test models some pretty complicated things, but a typical example would be, so say you had a system that you didn't necessarily have a fixed voltage on a boundary, but you had a resistance. And so this you would know that there's a resistor there and the system has maybe some current that flows in and out, and then there's a voltage that gets updated based on the current and the resistor of that system. Now that's a pretty simple one to start with, but because it's such the circuit module can handle so many different things, like once you can set that up, you can start adding complexity. Another one that might be a little bit more sophisticated would be a power boundary condition, where you would say that um, you maybe you have some nominal driving voltage of whatever that could be, 50 volts, but you know the system has a power limit as well. And if the current exceeds some value, then the voltage updates that to maintain a power limit, or it could be a fixed power value. So power and resistor are, of course, two pretty obvious uses. I've seen also the capacitor added, which helps. It can be like a stabilizing term and can also help mimic or help model some of the maybe nano features that would be hard to get in the mesh itself.
Great, thank you so much for that. The next question is, are EM, NS, and PIC solvers separate? How do they exchange fields and source terms in a space and time accurate coupling? For example, in CFD, Lagrangian particles have similar challenge.
Yes, can you repeat the first part of that question, the first sentence?
Yeah, are EM, NS, and PIC solvers separate?
Oh, I see. Okay. Yes. No, they work together. And it's a really neat problem, and it's a good point. The reference to the CFD. Basically, you would have, and the paper that I referenced before has a nice description of kind of the update. But yeah, the particles, you would start with some distribution of particles in your PIC system. And they don't actually have to know initially about the mesh, but we have to have the mesh to get fields. But and then they have some maybe spatial distribution that then is there's a process that's sometimes called scattering, where the charged particles that are in some volume description of space then get interpolated to nodes on the mesh. And that's basically a time step. And then the FEM part of it calculates fields based on that distribution. And then there's a reverse interpolation then for the fields to go back to the particles. And this just goes back and forth for as many time steps as a simulation would require. So it's just this constant back and forth of interpolation, and you have to be careful how you do the interpolation because of for the energy conservation. So it can be quite tedious in the actual implementation, but conceptually that's really it's kind of a straightforward update. There's a source for the FEM, and then the FEM creates fields that are then in the particles and propagate in the fields.
Great, thank you so much. And it looks like we only have one more question, and we have just enough time for it. This one is from Matt. He says that he is an EMC engineer, but I work with nuclear hardening engineers for space and strategic applications. I think I heard the right buzzwords, total dose, etc. Does Charge Plus have application for ionizing radiation applications?
Yes, that is something that we do calculate, ionizing radiation.
Great. Thank you so much for answering all those questions, Brian. And that brings us to the end of the webinar. Thank you, everyone. Following today's webinar, all registrants will receive an email from EMA with a link to the recording of this presentation. If you have questions about a particular section of interest to you, please feel free to reach out either through the ema3d.com website or email. Next up, look forward to the upcoming modeling discharges from human ESD up to high voltages using multiphysics simulation methods, another no-cost virtual event including several training workshops and technical discussions, which will begin this afternoon at 3 p.m. Eastern Time. Thank you all for your time and your attention, and have a great rest of your day.